Hi guys, Ajay here. In this video, we're going to start answering the question, what do we do when the test for divergence fails? In other words, when the associated sequence converges to zero. Let's get to it. So the answer is we look at something called the sequence of partial sums. So the nth partial sum of a series is the sum of the first n terms of that series. Of the series. Now that seems nice and innocent and easy, but it actually gets a little bit complicated. So to understand this, let's just think about it in terms of the different partial sums that we have. So the notation that we use is S. So I would say S sub 1 would be the sum from n equals 1 to 1 of A sub n. So I'm considering the series, the sum n equals 1 to infinity of A sub n. So that's an infinite sum. The first partial sum is just the first number. So in other words, it's the sum equals 1 to 1. So that's just A sub 1. And that's what's called the first partial sum. S sub 2 is what's called the second partial sum, and it's the sum from n equals 1 to 2 of A sub n. So that would be A sub 1 plus A sub 2, the second partial sum. S sub 3 would be the sum from n equals 1 to 3 of A sub n. So that's the sum of the first three terms, and that's my third partial sum. Now I could do this for all of the different numbers. I could actually go on and do it forever. So then S sub n, that's the sum, actually we'll call it S sub I. S sub I is the sum from n equals 1 to I of A sub n, which would be A sub 1 plus A sub 2 plus A sub 3 plus dot 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 and so on until we get to A sub I. This would be our ith partial sum. I can also think of it as my nth partial sum. It's just a random sum out in the future. So then S sub I or S sub n is basically just representing those first n terms. Sum of first n terms. Now, if you think about it, that first partial sum could be an approximation for the entire sum. Is it a good approximation? No, it's actually a terrible approximation, but it's still an approximation. So this is a bad approximation for the sum n equals 1 to infinity of A sub n. Now this second partial sum would be a better approximation, but still bad because I have one number, that A sub 1, but now I'm adding one of the other numbers. So I'm getting closer to the actual value when I add this other number. A better approximation but still bad. So then the third partial sum would be an even better approximation because we're adding another number. And then that ith partial sum, or the nth partial sum, will be even better. In other words, the more numbers I add, the closer I'm getting to the actual value of this series. The more numbers I add, the closer I'm getting to the actual value of the series. Okay, so in other words, I have one number. Yeah, that's a terrible approximation. I add something to it, still bad, but it's better because it's getting closer to the actual value. The more numbers I add from this whole list of numbers, the closer I'm getting to the actual value of the sum. So with this in mind, let's consider a sequence. So consider the sequence S sub n that is actually the sequence of partial sums. So this S sub n, I'm going to say, let's let that first partial sum be the first number. That's my bad approximation. Then the second partial sum is my second number in my sequence. That is the better but still bad approximation. So then S sub 3, which is getting closer and closer to the actual value, is a better approximation, and that's my third number in my sequence. And then we'll have S sub 4. And then this is an infinite sequence. We'll go down to S sub n, and so on and so forth forever. So the bigger n is, the better the approximation. So this sequence that I just created is the sequence of partial sums. So this sequence of partial sums is actually a really important sequence. It can also be thought of as a sequence of approximations for the series, where as n gets bigger and bigger, the approximation gets better and better. The sequence can also be thought of as a sequence of approximations for the value of the series, where as n gets bigger and bigger, the approximations get better and better. Okay, so take a second to absorb that because it's a little bit of a weird concept. We're saying, hey, look, as I add more numbers, I'm getting closer to the actual value. That makes sense, but then to turn it into a sequence can be a little bit confusing. Okay, so then my question for you is, what do you think happens if I evaluate the limit as n approaches infinity of S sub n? So the limit as n approaches infinity of S sub n. Give it a second, my writing has to catch up. There we go. Okay, so we know that as n gets bigger and bigger, the approximation gets better and better. So if we let n become infinite, it makes sense that therefore this would take on the value of the series itself. So this limit as n approaches infinity of S sub n should take on the actual value of the series. So, in other words, we're saying this sequence of partial sums is a really great way to understand what's happening with the series. So, in other words, if S sub n is the sequence of partial sums of the series n equals 1 to infinity of a sub n, then if the limit as n goes to infinity of s sub n equals to, I'm going to call it big S, and exists, then the sum n equals 1 to infinity of a sub n is equal to S, or rather it converges to S. If, however, the limit as n goes to infinity of S sub n goes to infinity, goes to negative infinity, or does not exist, then the series n equals 1 to infinity of a sub n diverges. So this is actually a really, really, really important idea. Yes. So we're going to leave that there for this video. We understand what a sequence of partial sums is. Now we have this idea about using the partial sums to determine if a series converges or diverges. So in the next video, we're going to talk about how important it is to recognize the difference between a sub n and s sub n, and also do some examples that hopefully make this make some more sense. All right, see you guys.